Now, both the techniques that we've looked at rely on revolving the shape. So you end up basically with circular cross sections. And of course, every circle is similar to each other. And so it works nicely. But obviously not all shapes have circular cross sections. If we can slice a shape in such a way that the shapes, may not necessarily be circular, but at least they're similar to each other, then we can use this same idea of adding up all the slices. So that's what we're going to look at, looking at volumes without the circular ones. So here's a rectangular pyramid. If I wanted to find the slice of that, I could slice it a couple of ways to get similar shapes. I could slice it, I guess horizontally would be the most logical way, and then each slice would be a rectangle. That'd be similar rectangles. If I was to slice vertically, we'd actually get a series of trapeziums. And we could probably do it that way as well, but I'm going to do it the logical way. So if I throw in a slice horizontally there, I need to basically come up with a formula in terms of, well, a third dimension now, z, so height. I'm imagining the number planes on the base. So I'm calling the third dimension height. And so I'm giving it a width of x and a height of y, our slice, and I need to get that in terms of the height, which I've called z. So there's my slice. Thickness now is in terms of z. I mean, I could pick any pronumeral I like. X and y is probably not a good idea if I'm using it for the sides, though. It needs to be different. So I know it's going to be x by y. How to get it in terms of? Well, what I do know, the area will be x times y, just like any rectangle. But that's no good to me at this stage. I could use similar triangles. So I'm going to find x in terms of z. So if I look at that triangle, the base obviously was b and the height would be h. And there's my slice. So I'm just looking at it in the direction of, which side was it? I've actually got some similar triangles because it'll be easy enough to show that those angles were the same because that slice is parallel to the base and so on. So there's one triangle. I'm just looking at the right angle triangle. So h and then the base would be half b. And then the other triangle, the base would be a half x and the height would be whatever h minus the z value is. I'm using z to represent height. So looking at the ratio of sides in those similar triangles, I've got h over a half b is the same as h minus z over a half x. Rearranging that, I get a formula for x in terms of z. Remember, b and h are constants. B was the base of the pyramid, h was the height of the pyramid. The way I like to do it is using coordinate geometry. So what I'm saying is, I need to get an expression for x in terms of z. Okay. So x in terms of z. Now, because this is a nice similar shape, it must exist a linear relationship between the two. I know at the height, the z value at the height is h. It's the complete height of the pyramid. The width of the slice at that point is 0 because I'm at a point. So I'm going to give that point up there the coordinates h0. Now at the bottom, at the base, now the height is 0 because I haven't moved any, and the width of the slice is b. So I've now got two coordinates. Well, I've got two coordinates. I should be able to come up with the equation of the line that joins those two. So my slope, which actually is going to be my x values in this case, because the second value there is going to be b minus 0 over 0 minus h. So x minus 0 will equal minus b over h, z minus h. And we end up with the exact same formula. Now, if you find it a bit unusual there, having x as the second pronumeral, it's okay, you can swap them around. I'm just calling them two letters. So you could have had xz and then swap these round and have 0h and b0. You're still going to come up with that same relationship between x and z. It's up to you how you label it. And then y, as I say, the only difference when we're looking at the y length is a is the base instead of b. So I know it'll work out to be a outside of h minus z over h. So multiplying those together, I now have a function for z in terms of z. A, b, and h squared and h, they're all constants. So I'm going to sum up all of those slices, and we're going from when it's 0 up to h. Okay, so AB over h squared, that's just a constant, so I'm taking that to the front. So I'm just finding the integral of h minus z all squared. Add 1 to the power over the power, but remember multiplied by minus 1 on the bottom of this fraction, coefficient of z. Subbing in, and there it is. ABH on 3, or as we, I guess, are more used to hearing it, 1/3 ABH is our volume. Another one, some of the other ones where they actually sit it on the number plane and give the base an equation. In this case, it's sitting on a circular base, and each cross-section is going to be a square perpendicular to the base. So I've got to try and draw a three-dimensional shape here. So I've put the XY base on the base. There's my circle. And every slice is going to be a square. And they've said perpendicular to the base, so it's perpendicular to the base. And there's another slice, there's another slice, there's another, and just doing all these slices. I'm trying to get a feel for what this shape actually is. And I'll just try and draw, yeah, a bit dodgy, isn't it? But well, I guess what you've got is a cone that's been shaved a bit. So it's gone over the top, a bike helmet maybe. All right, so my slice is a square. The thickness, the way I've drawn mine is in terms of x. It'll be as x changes. And the base there is twice the y value, which means the height is also twice the value. And so my area is 4y squared. But fortunately, we've been given an equation for this one already. We don't have to work one out. X squared plus y squared is 4. And so we get 4 outside of 4 minus x squared. And then it becomes like the others. So I'm going minus 2 to 2. But this one is a symmetric shape, so I can go twice 0 to 2. And a very simple integral. And there's our value. So it still uses the same idea. Basically, we've got to come up with an area of the slice. Once we've got that, we're just summing all the slices together from particular values. Here's an HSC one where one of the lines has somehow slipped over the top of the shape. That's rather unfortunate. Anyway. So our solid, it's cut from a quarter of a cylinder. The cylinder's radius r. The base is an isosceles triangle. So basically it's this little wedge in here we're finding the volume of. Okay. Isosceles triangle. AB is equal to AC, so they're the equal sides of the triangle. Length of BC is A, and they've labelled the midpoint capital X there. We're taking cross sections perpendicular to AX, and they're going to be rectangles. Rectangles in this case. So there's my rectangle. I'm just calling the thickness delta Z. And I'm going to call the length of the sides X and Y. So again, I've got this problem. How do I work out X and Y in terms of Z? So I know the area of my rectangle, of course, simple enough. It's just going to be X times Y. All right. So I'm going to find Y, first of all, in terms of Z. So if I just look at that part of the slice, so I'm now looking at the end of the quarter cylinder, I'm looking into the shape. And so that's what I'd see. I'd see this DAX. The slice would be going vertical, and there's my thickness. And so I'm doing it in terms of coordinates, but the coordinate of the slice at the top will have some Z value and some Y value. Z representing the length along AX, and Y representing the height of the slice. Now, up at the top, I'm giving that the coordinates 0, R. Okay? So I'm imagining I'm starting over here at A. And so my slice hasn't moved along at any point, but the height of the slice is R at that point. And I'll keep going until I get to X, where now the slice is R along, but the height of the slice is now 0. Because all I'm saying is, how far is that slice along the perpendicular height? And how high is it at that point? And so really all it is the equation of a circle. If you think about it, look at the coordinates. It's a circle. But we'll put it as the semicircle, because the height will be the square root of r squared minus z squared at any particular point. Okay. Now we have to look in the other direction to get the x. What's that going to look like? So to find x in terms of z, well, I'm actually going to look down on the shape. And if I look down, remember, it's sitting on an isosceles triangle. And that isosceles triangle is ABC. And the slice would be there. So all I see, if I'm looking down, I see the isosceles triangle, and I'd see a horizontal slice there. How do I get that in terms of? Well, let's give it some coordinates again. Now I'm saying, okay, I want to find z in terms of x. So I'll call it zx at any particular point. Up at the top, it's now 0, 0. I can't change the z value from over here. So when it's at A, which was over here on the left-hand side, we have already determined that the z value is 0 at that point. So it's still 0 at that point. Now, how wide is my slice at that point? Well, 0, because it's at the point. When I get to the end, we know the z value is r. How wide is it? Well, it'll now be the width of the base of the triangle, RA. So the relationship I'm looking for is between those 2 points. This one is just a straight line because essentially I'm just finding the equation of this line. That's what I'm doing. So the slope would be A over R, subbing it into our point slope formula, and we get x is AZ on R. All right, so I now have an expression for x and y in terms of z. AZ on R times the square root of R squared minus Z squared. Playing around with it, so times our thickness Z for delta V. We're summing from 0 to R, 0 to R, of AZ on R, square root of R squared minus Z squared. So my integral, well, the A over R, I'll take out the front. I've got Z outside the square root of R squared minus Z squared. I can just make this a root U du, can't I? Because I've got Z out the front. Z's part of the derivative of minus 2Z. So that should integrate then to give me, well, playing around with it, let's create the derivative out the front to make it more obvious. There's minus 2Z. So we've got 2/3 R squared minus Z squared to 3 on 2. Sub in 0, sub in R, and we come up with our volume. That's probably one of the harder ones that's appeared over the years, to be honest. I think the reason that one was harder, and there you go, the average for that question that particular year, 1.01 out of 4 marks for that question. And I think the reason it was harder is because the vast majority of these similar cross-sections are linear relationships, so you're looking for just an equation of line. But it was that one where this part wasn't linear because you looked into it and you ended up with a circle rather than a straight line. Look, there's lots of different shapes. I mean, we could do stacks of different examples for different shapes, but there's nothing better than just having a go at them. And we may end up doing a whole heap on the board just to explain them. But if that's what we have to do, that's what we have to do.